Hello friends, I am Dr. Deepakar Patil, working as Assistant Professor and Head Department of Electronic Science, SNJB's KKH Arts, SMGL Commerce and SPHJ Science College, Chandwad. Today we will see one of the topic of the second paper EL 232 Digital System Design for the SYBSc Electronic Science. Here we can see the syllabus. In this first unit is the logic families, and first topic is the revision of the logic gates using the diodes, transistors and the MOSFETs. Now today's presentation is based on this topic. Friends, we know there are the different gates used in the digital systems. If we classify these gates, the classification divides these gates into the three different parts. One is the basic logic gates, second one is the universal logic gates, and third one is the other logic gates. In basic logic gates, there is a NOT gate, AND gate and a OR gate. In universal logic gates, there are the NAND gate and a NOR gate. Other logic gates which are frequently used, these are known as the XOR gate and the XNOR gate. Today we will see basic logic gates in the details. As you can see on the screen, there are the different symbols and as well as the truth table for the different gates. First of all, we will see the NOT gate. NOT gate is a very simple gate. It has only one input as shown in the figure. A is nothing but the input of a NOT gate and Y is nothing but the output. So NOT gate has one input and one output. As shown in the truth table, A and Y. So A has two different values, 0 and 1. If A, that means input A is a 0, output Y is a 1, and when input A is 1, output is a 0. That means NOT gate complements the output. Now we can define a NOT gate as the output of the NOT gate is a complement of the input. Second gate is the AND gate. Here we can see that there are the two inputs to the AND gate, A and B, these are the inputs and Y is the output. As shown in truth table, there are the two inputs, that means 2 raised to 2, four different input combinations are there in the truth table of the AND gate, 0 0, 0 1, 1 0 and 1 1. Now what is the output of the AND gate? It is nothing but the logical AND, that means 0 and 0, the output is a 0. 0 and 1, output is a 0. 1 and 0, output is a 0, and as shown in the last row of the truth table, 1 and 1, output is a 1. That means whenever there is a 0 available on single input or as well as the both input, output is the 0. Now can we define AND gate? How can we define AND gate? So we can define AND gate for 0 as well as for 1. That means there are the two definitions. Now first definition, we will define AND gate for the 0. The output of the AND gate is 0 when one or more than one input is a 0, as shown in the first three rows of the truth table. Now just define AND gate for the output 1. So output of a AND gate is 1 when all the inputs are at logic 1. Okay, so this is the definition of the AND gate. Now next gate is the OR gate. As in case of the AND gate, OR gate also has a two input, A and B, and only one output. As shown in the truth table, 0 0, this is the first input combination. For this, output is a 0. Second input combination 0 1, output is a 1. That means it follows the OR laws of the Boolean algebra. Third row shows that 1 or 0, output is a 1, and fourth row shows that 1 or 1, output is a 1. Now again we can define OR gate for the 0 as well as for the 1. So there are the two definitions of the OR gate. Now just first of all we define the OR gate for the 0. The output of the OR gate is 0 when all the inputs of the OR gate is at a 0. Now define OR gate for the output 1. So output of the OR gate is 1 when only one or more than one inputs are at logic 1. Okay, that's it. for the definition as well as the symbol and the truth table of the basic logic gates. Okay. Here we see a NOT gate biasing the bipolar transistor. Now, what is the circuit diagram? One may ask that what is the circuit diagram of the NOT gate, what is the circuit diagram of the AND gate and OR gate. So, in this slide we will see how to fabricate NOT gate biasing the bipolar transistor. Okay. So, this is the circuit diagram of the NOT gate biasing the transistor. As we see, there is a transistor Q1, emitter of the transistor is connected to the ground, input A is connected to the base of the transistor through the resistor R, which acts as the current limiting resistor. Collector of the transistor is connected to the plus VCC through resistor R, and output is taken at the collector of the transistor. Now, how it acts as the NOT gate? Let us see. Suppose A is a 0. 0 means a 0 volt is connected to the input A. When we connect a 0 volt, base emitter junction of a transistor Q1 is reverse biased. That means transistor is a off, or we can say it is a cutoff. That means it is an open circuit. If we measure the voltage at Y, that means ground and Y, we are measuring actually the voltage across the open circuit, and we know if there is a open in the circuit, all the voltage of the circuit is available across the open. Hence, at Y, all the voltage of the circuit, that means the 5 volt, is available at the output, and that 5 volt is treated as a logic 1 in a digital electronics. That means when input is a 0, output is a 1, and this is nothing but the first row of a truth table as you see on the screen. Now, in second case, when A is 1, 1 means a 5 volt is applied at the input. When we apply a positive 5 volt, base emitter junction of a transistor Q1 becomes a forward bias. That means current flows from collector to the emitter. Okay. Means if we measure the output, that means at the Y with respect to ground, we are measuring the voltage across a short circuit, and we know across a short circuit resistance is a 0. That means the voltage is a 0 volt, and that 0 volt is treated as a logic 0 in the digital electronics. Hence, we can see that when input is a 1, output is a 0, as shown in the last row of the truth table of the NOT gate. Next, before we switch over to the NOT gate biasing the MOSFET, let us just revise what is the MOSFET and how it acts as the on switch and off switch. Now, this is the symbol of the MOSFET. There are the two types of the MOSFETs. One is the N channel MOSFET, another one is the P channel MOSFET. Okay. For the N channel MOSFET, as shown in the figure, when 5 volt is connected at the gate, that MOSFET becomes on. That means on switch. When we apply a 0 volt at the gate of the MOSFET, N channel MOSFET, it becomes a off switch. Exactly opposite situation is there for the P channel MOSFET. In case of the P channel MOSFET, when we apply a 0 at the gate of the P channel MOSFET, it acts as the closed switch, that means on, and when we apply plus 5 voltage at the gate of the P channel MOSFET, it acts as the open switch, that means off. And this is the basic for the circuits which uses a MOSFET as the main element. Next circuit is the NOT gate biasing the MOSFET. Yes, we can fabricate a NOT gate biasing the MOSFET, and here is the circuit diagram. Here you can see that there are the two MOSFETs are used. One is the Q1 MOSFET, which is nothing but the P channel MOSFET, and another one is the Q2 MOSFET, that is nothing but the N channel MOSFET. The gates of the MOSFET are connected together, and it is given input is given to the common gate. Output is taken across the drain. Plus 5 volt is connected to the source of the Q1, and source of the Q2 is connected to the ground. Okay. What happens when we connect a 0 volt to the input? When we connect a 0 volt to the input, as we have seen in the basic, transistor Q1 is on, that means P channel MOSFET is on, and Q2 MOSFET, that means N channel MOSFET, it acts as the off switch, just like this one. Okay. Now, what is the effect of this one? Now, the current flows from plus 5 volt to the drain of the N channel MOSFET, but N channel MOSFET is the off switch. If we measure the voltage at Y, that means voltage at Y with respect to ground, that means we are measuring the voltage across the open switch. Okay, and that means, as we know, all the voltage of the circuit came across the open. Here the voltage is 5 volt and we are measuring the voltage across the open. That means output is at the plus 5 volt, and that plus 5 volt is treated as the logic 1. Hence, when input is a 0, output is a 1. As again you can see this in the first row of the truth table. Now, in a second case, when A is a 1, that means 5 volt is connected to the MOSFET, what actually happens? See, when plus 5 volt is connected, transistor Q1 becomes a off. That means P channel MOSFET becomes off and N channel MOSFET becomes on. Now, if you measure the voltage at the output Y, that means we are measuring voltage across a closed switch. But in this case, no current flows from plus 5 volt to the Y. There is no voltage, no current. Obviously, if there is no voltage and no current, you will get the 0 voltage at the output. Okay, and this is nothing but a logic 0 available at the output. That means when input is 1, output is a 0, as shown in the second row of the truth table. And this is how we can fabricate NOT gate by using the MOSFET. So, we have seen that NOT gate can be fabricated by using the bipolar junction transistor as well as by using the MOSFET. And this is all from today's presentation point of view. In the next presentation, we will see the different circuits for the AND gate as well as for the OR gate. Thank you.